My name is Philip Nell and I will be presenting my final year project titled Wave Drag Reduction of a Winged Slender Body at Transonic to Supersonic Speeds. My supervisor is Professor van der Spuy. Aircraft experience a significant increase in drag force when accelerating through the transonic regime. In order to minimize shockwave drag at transonic speeds, the variation in cross-sectional area should be smooth, since Mach planes intersect a body in the direction normal to the flow at Mach 1. This is called the transonic area rule. An example of applying the area rule to a winged body is to decrease the cross-sectional area of the fuselage at the onset of the wings accordingly, as depicted in the figure. When designing an aircraft body with the aim of efficiency, the application of the transonic area rule may be of importance to decrease wave drag. In this project, the effectiveness of applying the transonic area rule to a winged body is investigated. The project objectives are to investigate the effectiveness of applying the transonic area rule to a winged body in order to reduce shockwave drag for Mach numbers ranging between 0.8 and 1.2 by means of computational fluid dynamics and an experiment. In order to do this, the existing supersonic wind tunnel setup had to be modified such that drag tests can be conducted. The use of Schlieren imaging to capture the formation of shockwaves over different winged body designs at different Mach numbers. The design of a nozzle able to produce Mach numbers in the range of interest, and the use of computational fluid dynamics to capture the shock structure for a comparison with experimental Schlieren images. Shown here are the different models to be considered. The drag force result from the area-ruled winged body is to be compared with that of the winged plane body. According to theory, the winged plane body is to experience higher drag force, and the body of revolution should have similar wave drag characteristics as the area-ruled body, since the variation in area is equivalent normal to the flow direction. The models were 3D printed for the experiment. This image conveys the small size of the models, with the fuselage diameter being 1.56 mm. The Sears-Haag formula was used for the profiles of the support and trailing faces of the sting to which models are attached in order to minimize their effect. Seen here is the area-ruled body attached to the support. The support is connected to a load cell in a housing. The designed nozzle and the parabolic mirror illuminating the test section through the light source can also be seen. A computer and data logger is used to log data from calibrated pressure transducers and a load cell. A DSLR camera is used with the Schlieren imaging setup. A convenient feature of the experimental setup is being able to have a live view of the Schlieren imaging while varying the flow rate from the valve. The Schlieren images of the flow for the different models as the Mach number is increased will now be shown. In this inverted image, darker regions indicate denser regions. The first notable shockwave forms at the first location where the area of the body reaches a maximum normal to the incoming flow. This is due to the nose cone of the body acting as a nozzle, accelerating the flow to sonic conditions before the free stream Mach number has reached sonic conditions due to confinement of the flow between the body and the neighboring flow. This occurrence is analogous to the formation of a shockwave above an airfoil at high subsonic freestream conditions. As the flow reaches supersonic conditions at the downstream edge of the nose cone due to confinement, expansion waves emanate from the edge. The observed shockwave is the consequent recompression wave, as supersonic conditions over the bodies are not yet sustainable at the particular freestream Mach number. As the freestream Mach number increases, the expansion fan becomes stronger, moving the recompression wave downstream, as seen for increasing Mach numbers. The differences between the shock structures for the models can already be noted around Mach 0.95. For the winged area-ruled body, weak expansion waves, noted mainly due to the subsequent recompression waves, can be seen to form on the backward-facing geometry. Furthermore, weak compression waves form on the forward-facing geometry, as well as for the winged plane body, where shock waves form in the vicinity of the wings. Since the body of revolution has no wings, no such shock waves can be seen to occur. From the formation of a normal shock at the nose tip, it can be deduced that the free stream has already reached sonic conditions. As the Mach number further increases, an oblique shock forms at the nose tip. It can be seen that recompression waves disappear much earlier for the winged area-ruled body than for the winged plane body, with the winged plane body still displaying relatively strong recompression waves at Mach 1.15. The disappearance of recompression waves signifies the onset of a dominant supersonic regime over the entire body. It should also be noted that, apart from the recompression waves from the cone edge and nose tip, the winged plane body displays a significant third recompression wave that is much stronger than the weak recompression waves displayed by the winged area-ruled body. As expected, no additional recompression waves are visible for the body of revolution. From this discussion, it can be suggested that the body of revolution is likely to have the least wave drag and that the winged area-ruled body is likely to have less wave drag than the winged plane body. Important for the interpretation of drag results are strong compression waves at the onset of the vertical arm support downstream of the model. These compression waves are indicative of oncoming supersonic flow, and increase in strength as the recompression waves over the models start to become weaker and the flow over the models becomes dominantly supersonic. As expected, the re-entry vehicle displays a strong detached bow compression wave. Also notable are clear expansion fans emanating from the trailing edge of the spherical face of the re-entry vehicle and their consequent recompression waves and reflections downstream. This image shows the formation of shock waves over the winged area-ruled body in the transonic regime obtained by an inviscid CFD simulation. This CFD simulation reveals noteworthy similarities and differences between the Schlieren imaging technique and CFD contour maps. The results are analogous to the shock structure as seen during the experiment through Schlieren images. This is a comparison between Schlieren imaging, a CFD density map, and a CFD Mach number map. Comparing the Schlieren image with the CFD Mach number map, it can be deduced that expansion fans emanating from the model geometry are unclear in the Schlieren image. This may be due to the fact that expansion fans from slender bodies are weak and gradual, making them less noticeable than oblique shocks or recompression waves. Examining the cone recompression wave on the Schlieren image, what appears to be the shape of an expansion fan is most likely not the expansion fan, but the onset of recompression of weaker expansion waves from the expansion fan. Keeping in mind that orange to red indicates higher Mach numbers, the onset of recompression can be seen from the Mach number map, where a lighter triangle appears slightly downstream of the red area. This means expanded flow versus slightly recompressed flow, but still supersonic. Although unclear from the Schlieren image, the likely location of the onset of the expansion fan is shown. It can be concluded that the range of refracted light blocked by the knife edge is such that weak expansion fans are unclear. These are the experimental drag force results. The steep drag rise due to compression at the support is clearly visible. Considering the discussion on shock waves produced by the three different slender bodies, as well as the drag test results, it can be reasonably suggested that the body of revolution has the least wave drag, followed by the winged area-ruled body, and that the winged plane body experiences the most drag, despite having the same length and frontal area as the winged area-ruled body. For interest's sake, the drag force experienced by the re-entry vehicle model arm assembly peaked around 80 grams. The effectiveness of the area rule cannot be concluded from the experimental drag results, since the effects of the sting and arm support are inherent to the results. In order to investigate the effect of area ruling on the winged plane body, this CFD simulation considers the models in free flight and in shockless oncoming flow. The flow field from the body of revolution is considered as the baseline flow field. In order to better visualize the added shock structure and relative strength of the shock waves caused by the addition of the wings and the application of the area rule, this flow field is subtracted from that of the winged area-ruled body and the winged plane body. Area ruling the fuselage allows for less confinement of the local flow between the body and the free stream, resulting in less compression. This is due to the effective flow area being larger. It is clear that the shock waves generated at the leading edge of the wings are stronger for the winged plane body than for the winged area-ruled body. Since the body is forced through the air and compression requires energy, more thrust is needed to propel a body which is generating strong shock waves as opposed to one generating weaker shock waves. The oblique shock as seen through contours of Mach number on the vertical plane for the winged plane body is strong enough to reduce the flow speed to subsonic conditions for a significant distance away from the body. For the area-ruled body, it is not strong enough. Supersonic flow persists downstream of the weaker oblique shock, impinging on the forward-facing geometry of the fuselage near the trailing edge of the wings. This leads to the additional oblique shocks in the vicinity of the middle of the wings, which are unique to the flow field of the winged area-ruled body. Unlike the experiment, the CFD drag force results considers only shockwave drag and ignores viscous drag. As demonstrated by the experiment, the body of revolution has the least drag, followed by the winged area-ruled body. The winged plane body experiences the most drag. The CFD results show a steep increase in drag force around Mach 1. As expected, this gradient decreases when moving from the transonic regime towards the sub or supersonic regimes. The CFD simulation for drag results is sufficiently mesh independent. The differences in results obtained by successively refined meshes are negligible. It was noted that as the mesh is refined, the wave drag at Mach 0.8 tends toward a number close to 0. As expected, the wave drag characteristics of the winged area-ruled body tend towards those of the body of revolution, since the drag curves are of similar shape. Both experience a decrease in average gradient from around Mach 1, followed by an increase at around Mach 1.05, as opposed to the winged plane body, for which the gradient from Mach 1 to 1.1 appears to be relatively constant. It may also be suggested that the drag divergence Mach number for the body of revolution and the area-ruled body is approximately the same, and somewhat higher than that of the winged plane body. Comparing the free-stream CFD simulation with experimental Schlieren results, it can be seen that due to the absence of a fluid boundary around the body for the CFD simulation, no normal shock occurs upstream of the body before the oblique shock at Mach 1.05 emanates from the nose tip. As the Mach number was increased for the experiment, this normal shock moved downstream, interacting with the oblique shock from the nose tip at Mach 1.05. Also due to the absence of a fluid boundary significantly close to the body, in other words a larger effective flow area, recompression waves disappear at lower Mach numbers for the CFD simulation. Furthermore, of course, due to the backward facing geometry as a result of the absence of a sting used in the experiment, expansion fans emanate from the trailing faces of the slender bodies. This results in an additional recompression wave, which can be seen to move toward the trailing end of the models as the Mach number increases. Before moving on to the conclusions, shown here are Schlieren images of an extra study done as part of the project of a normal shock in a nozzle to provide experimental data for possible future use, discussed in the report. The application of the transonic area rule decreases the shockwave drag by an average of 15% between Mach 1 and 1.2. For the models used, shockwave drag is negligible between Mach 0.8 and 0.9 and starts to become significant around 0.95. The average of the wave drag reduction for the data points at Mach 1 and Mach 1.05 for the CFD simulation is 30%. Using Richard Whitcomb's results to estimate the ratio between wave drag and total drag, it is likely that the application of the area rule to the winged plane body reduces the total drag between Mach 1 and 1.05 by about 10%. The Schlieren imaging proved to be very effective for capturing the formation of shock waves over the models, as well as the location of a normal shock in a nozzle. The Schlieren imaging was clear enough to be able to identify crucial differences in shock structure of the flow over the models. The CFD shock structure results are analogous to results obtained by the Schlieren imaging. The project proved to be very satisfying in terms of experience gained and from an academic point of view.